Good evening, Dumfries. This evening, we're talking about dark matter, and I'll be trying to answer the questions: why is it dark, and does it matter? So it's been quite a long time now that we've known that the universe has a dark side. Roughly 100 years, perhaps a little longer than you think. And this little cartoon sums it up quite nicely, where the lecturer, professor at the front there is saying, after the discovery of antimatter and dark matter, we have now confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever. So I hope to convince you that dark matter does indeed have an influence on the universe, even if we don't really understand what's going on. So if we take all the stuff in the universe, all the matter that's out there, and we subdivide it into stuff we know about and stuff we don't, we get this pie chart. 16% of the matter in the universe we have a reasonable handle on. If you ask yourself what is that 16%, you might assume that, well, it's all stars and galaxies, presumably. Well, stars actually only account for a relatively small amount of that 16%. Only 2% of the universe's mass is made up of stars. You can see there that there's actually far more simply hydrogen and helium gas floating around than the total amount of mass in the stars. That final sliver of 1% is other particles like neutrinos, and I'll mention those a little later. But returning to the left-hand side, 16% we understand. So this evening we're really addressing what is that? What's the other 84% of the universe made of? So I'll be trying to address the questions: why is it dark? What's the evidence that we have that it exists? And there are nominally 4 strands of evidence, each independently pointing us towards the existence of dark matter. I've got enough time this evening to describe the first 3. I think I'll leave the 4th one. It'll be in the handout of the slides, which I'll make available to you later. But I'll be going through the first 3 of those 4 pieces of evidence, and then asking the question, well, if it exists, what actually is it? And there are 2 candidates, machos and wimps. I'll explain what those are in due course. And finally, we'll ask the question, well, does it really matter? So, question 1, why is it dark? Well, the simple answer of why it's dark is because it's not light. And that's a bit frivolous. Let's give a slightly more useful answer. Why is it dark? Well, it's dark because it does not behave the same way as what we can call normal matter, or perhaps ordinary matter. So ordinary matter, the stuff we're familiar with, everything we see around us on the Earth, in the solar system, in the Milky Way, etc., all of the stuff we can see interacts through the electromagnetic force. In other words, it's made of atoms which have electric charge. And because ordinary matter interacts through the electromagnetic force, it means atoms emit and absorb electromagnetic waves. And here we're using the word light in the broadest sense to mean any wavelength of electromagnetic waves, whether that's visible light, ultraviolet, X-ray, gamma ray, infrared, microwave radio, it doesn't matter, it's all electromagnetic waves, but let's just refer to it as light. And hence, ordinary matter can be detected through its interaction with light. Because it emits or absorbs light, we can observe light and hence deduce the existence of ordinary matter. But dark matter does none of these things, and that puts it into a completely different category than ordinary matter. So everything we see around us, everything that's familiar to us, is made of atoms. And because, well, this picture of an atom isn't strictly accurate, quantum mechanics tells us atoms don't quite look like that, but it's good enough. This model of the atom has got a positively charged nucleus, positively charged particles in the nucleus, and negatively charged electrons buzzing around the nucleus, like bees in a beehive. So because we've got positive charge and negative charge moving, that can generate electromagnetic waves, either by emitting them or by absorbing them and changing the state of the atom. So electromagnetic waves are fundamentally linked to the existence of atoms. So let's have a look at the evidence that tells us there's something out there which is apparently not made of atoms. Let's first look at galaxies in clusters. And we can ask ourselves, what is it that holds galaxies together in clusters? When we look out into the universe with ground-based telescopes or the Hubble telescope or the James Webb telescope, we see enormous numbers of galaxies which often occur in clusters or perhaps even superclusters. So what is it that holds these clusters together? And the answer is gravity. It's not a trick question. Gravity is holding all of these things together. Now we know gravity depends on mass, and mass can be estimated for any given galaxy simply by effectively counting the stars. If we measure the brightness of any given galaxy, then we can say that, assuming we understand stars, and generally we understand the evolution, the birth, the life, the death of stars, if we understand stellar evolution, then if we know the total brightness of a galaxy, then we can estimate the number of stars it must have. Because we can sort of say, well, the average star has this brightness, and we know how many stars there are, how many bright stars, how many dim stars, we know what the average is. So if we know the total brightness, we can estimate the total number of stars in the galaxy. And by the same argument, if we know how many stars there are, we can estimate the mass of all of those stars. Some stars are more massive than others. We have giant stars and we have dwarf stars. But knowing the evolution of stars, we can get a reasonable estimate for the average mass of all of the stars, and hence we can get an estimate for the mass of the galaxy. So yes, there are some assumptions in there to go from the brightness of a galaxy to go to the mass of a galaxy. But most of these things are fairly well understood, and I've said here that we get a rough estimate of these things. But the rough estimate might be within a few percent or within 10%. It's not going to be wrong by an enormous factor. So if we can take a galaxy, measure its brightness, and from that get its mass, we can do that for all the galaxies in any given cluster, and hence we can work out an estimate of the mass of the cluster itself. And if we know the mass of the cluster, we know the strength of the gravity that's holding it all together. As early as the 1930s, not quite 100 years ago, it was realized that if you do this and calculate the gravity in this way, it's not enough to keep the cluster together. In other words, the cluster should have drifted apart. If the only gravity that's present is the gravity due to the mass of the galaxies that we can estimate from their luminosity, the cluster should have drifted apart a long, long time ago, and we shouldn't see all of the galaxy clusters that we see in the universe. Something is wrong. The luminosity, or at least using the luminosity to find the mass, appears to underestimate the mass that must be present, not by 10% or 20% or 50%. It seems to underestimate the mass by a huge factor. A factor of 2, a factor of 3, a factor of 4, a factor of 5, or possibly even more. There's a huge discrepancy between the mass that we deduce must be there to hold the cluster together and the mass that we can see in the luminous galaxies. Here's a phrase that I'm going to use more than once. It's as if there is some additional mass that is not luminous, mass that we can't see, that is providing the extra gravity that is needed to keep the cluster intact and bind the galaxies together. What is this additional mass? Well, we don't know, but let's call it dark matter, because that sounds pretty cool. Let's look at an independent second strand of evidence, not galaxies in a galaxy cluster, but stars within a galaxy. All galaxies rotate to some extent or another, and we can work out how fast the stars are moving using the Doppler effect. The idea that if we've got light from a star and that star is moving away from us, the light from the star gets redshifted, whereas if the star is moving towards us, the light from the star gets blue shifted. So if we can measure the spectrum of any given star, we can work out its radial velocity, its velocity towards us or away from us. It doesn't give us the side-to-side velocity, but it does tell us the velocity along our line of sight. So if we look at this cartoon on the right, if we've got a galaxy that's rotating, we may not be able to tell from the galaxy which way round it is, in other words, which of the spiral arms are coming towards us and which are away from us. But if we measure the spectrum of various stars, for instance, at location A and location C, we'll see some of them are coming towards us. For instance, in this cartoon, all of the stars around A are coming towards us and all of the stars around C are going away from us. Any stars near the middle are moving sideways, and so they don't give us a very clear Doppler shift. So we wouldn't want to choose a face-on galaxy like this one, because most of the stars are moving in the plane of the sky, as it were. Very few of those stars are coming directly towards us or directly away from us, so they don't have a very clear Doppler shift. If we look at a galaxy edge-on, then certainly some of those stars on one side or the other will be coming towards us or away from us, but notice this rather dark dust band down the middle of the galaxy. Many disk galaxies have this dust down the middle, and that makes it more difficult to see the stars. So edge-on is not ideal either. So we choose a galaxy that's at a jaunty angle, not quite face-on, so that some stars are moving towards or away from us, and not quite edge-on, where the dust starts to get in the way. And if we were to examine stars in a galaxy like this, we would find some of them red-shifted, some of them blue-shifted. So this picture on the right is not supposed to indicate the colour of the stars, it's supposed to indicate which way the spectrum would be shifted because of their velocity. So the middle ground there, the one that's sort of a greeny colour, those are stars where we can't really get a clear Doppler shift. So what do we expect to see for orbital velocity? If we were to measure the speed of stars going around a galaxy, what would we expect? How should it vary if we look at stars further and further from the centre of a galaxy? If all the mass keeping an object in orbit is inside the orbit of that object, then we would expect the speed as a function of distance to look like this. Here we're using as an example the speed of planets going around the Sun. The vertical scale is the orbital speed in kilometers per second, and the horizontal axis is the distance from the planet to the Sun, measured in astronomical units. And you can see that planets close to the Sun travel very fast, and planets a long way from the Sun travel much more slowly. If we wanted to, we could plot this on a logarithmic plot and we get a nice straight line, but let's not worry about that. Let's just plot it in the usual way, a linear scale of speed as a function of distance. So all of these planets are in orbit around the Sun, and essentially all of the mass of the solar system, or at least 99.9% of it, is concentrated in the Sun. The planets have very little mass of their own compared to the Sun. And if we were to look at a star a long way from the centre of a galaxy, where most of the mass of the galaxy is within the orbit of the star in question, then we would expect the velocity curve to look a little bit like this. So let's have a look at what we actually see. Let's measure some Doppler shifts to get the velocity of stars, and again this graph is showing on the vertical scale the speed of a star, and the horizontal scale the distance of that star from the centre of the galaxy. Now, if we think about stars very close to the centre of the galaxy, we have to remember that a star that's very close will have not that large a mass within its orbit, because quite a lot of the mass of the galaxy is outside the orbit of the star. So to start with, when we measure the speed of stars, we find it tends to grow as we go out towards the edge of the galaxy. And in this particular case, most of the galaxy appears to be within that red ellipse, simply from judging that most of the light of the galaxy appears to be coming from within that red ellipse, and there don't seem to be many stars outside. It would appear that 99% or more of the mass of the galaxy resides within that distance of about 15,000 light years. So once we start thinking about stars that are any further out than that, well, effectively all of the mass is within the orbit of any star that lies out here. And so we would expect to start getting the same sort of curve as we saw for the planets in the solar system. We would expect the speed to start to decrease as we're getting further and further away from the galaxy. Now, unfortunately, the number of stars we can pick on gets very, very few because, of course, we're now talking about outside the visible disk of the galaxy. So there's very few stars that we can measure out here to find out what their Doppler shift is, to continue this curve to see if it starts to come down. But although there's very few stars, there's actually plenty of gas out there, and we can measure the Doppler shift from molecules or atoms of hydrogen. It doesn't really matter what the object is, it doesn't matter whether it's a molecule or an atom or a star, we can still work out how fast it's travelling from the Doppler shift. So what do we find when we extend the yellow curve out from that point of 15,000 light years? Does it start to decrease? No. It either levels off or in some cases actually increases. So this is indicating that hydrogen gas way out here, a long way from the centre of the galaxy, is travelling much faster than you would expect. So what is it that's holding these gas molecules or gas atoms in their orbits? Something must be holding them, otherwise the hydrogen would have disappeared a long time ago. So again, it appears as if the mass keeping these stars and atoms in orbit around the galaxy is much more than we can account for from the luminous disk of the galaxy itself. There we go, the same phrase again. It would appear as if there is some additional mass, not luminous because it's not accounted for by all the stars we can see. Additional mass is providing the extra gravity needed to keep the stars, or the gas atoms, orbiting at high velocities, even a long way outside what we would declare as the visible edge of the galaxy. So it looks like another piece of evidence for dark matter within the galaxy. If we think of a cartoon of what that means, if we've got a galaxy rotating without dark matter, what we would expect is to find the stars moving quite quickly close to the nucleus, but much more slowly on the outer edge. This is just a short video which resets and hence glitches every few seconds. But the important thing is fast in the middle, slow towards the outer edge. But that's not what we actually see. What we actually see is fast in the middle and fast on the outer edge as well. In other words, if we think about what's actually happening, we would expect the outer stars to move slowly. What we actually find is the outer stars move quite quickly. And we can only understand what's going on the right-hand side if we say, well, there must be dark matter in there as well as the visible matter that we can see in the galaxy itself. Let's have a look at a third strand of evidence, gravitational lensing. This is quite unlike the previous two. We can calculate mass from its gravitational effect, not on galaxies in a cluster or stars in a galaxy, the previous two strands of evidence, but looking at the effect of gravity on light itself. Yep, I know, I've already said that dark matter does not interact with light, yes. But even though it does not emit light or absorb light, it has mass. And if it has mass, it has gravity, and if it has gravity, then it can bend light from other stars or galaxies. And if we look at this particular cartoon, we can imagine that we are on Earth observing a very distant galaxy. And that galaxy, the light from the galaxy, well, some of it might travel in a straight line towards Earth, But on passing through this big galaxy cluster, which happens to be between us and this more distant galaxy, the mass of this galaxy cluster is bending the light and focusing it towards Earth. If you prefer, you can think of the galaxy cluster as distorting space, and that distorted space results in the curvature or bending or focusing of light from this distant galaxy. And sometimes this is what you get. A foreground galaxy, such as this orange one right at the middle, can bend the light from a more distant galaxy, and here a distant bluish galaxy is being distorted, very distorted, into a horseshoe, looking nothing like the original galaxy. At first it might be a little difficult to imagine how can you distort light into a horseshoe like that, or into a complete circle sometimes. But if you think about a rather bad lens, such as, for instance, the base of a wine glass, you can see why. Here's a light source, which is effectively not quite a point source, but it's one source of light. If you allow the light to shine through a very poor quality lens, such as the base of a wine glass, you see that the individual light is split up and it might produce little arcs of light. Here it's producing sort of 2 arcs, here it's producing 3 arcs, and if you hold the lens at just the right angle, you might actually get the light spread out into a horseshoe or maybe even a complete circle. So this shows you how a lens can distort light from a more distant object. So next time you're having a romantic candlelight dinner with your loved one, make sure you hold up the wine glass to a candle and see gravitational lensing in action. And when we look out into the universe, it really doesn't matter what telescope we use, whether it's the Hubble or the latest images from the web. If we have a whole load of galaxies in a cluster producing a very large mass that can distort the light from more distant galaxies, then those distant galaxies can end up distorted into arcs, like we saw with the wine glass and the candle, and very distorted, messy arcs. In this particular case, no horseshoes, but lots of distorted galaxies from the background due to the mass of the intervening galaxy cluster. And these distorted images effectively tell us about the mass distribution in the lens, in other words, in the galaxy that is producing this lensing effect. Now, it's relatively easy to say, if I've got this mass, how will that then bend light and produce a distortion of a more distant galaxy? It's actually a lot trickier to do it backwards and say, given that this is what the galaxies look like, given this is how they're distorted, can we work out what mass there must be in the lens in order to produce that distortion? It's a much trickier problem, but it can be done with a large enough computer. And when we find how much mass is there in the galaxy cluster that produces the distortion we see, the amount of gravitational lensing, we find the mass that must be there is more than we can see in terms of the luminous galaxies themselves. There we go again. It's as if there is some additional mass that is not luminous, that's providing the extra gravity that is needed to bend the light and produce the distorted images that we see. Yet again, more evidence for dark matter. Okay, I'm going to skip over piece of evidence number 4. I hope you're already convinced that there is evidence that there is something out there. There's actually a lot of evidence that there's something dark out there, but that doesn't answer the question, what is it? Well, it's thought that there are 2 main candidates for what dark matter might be. Machos and WIMPs, and I'll explain those in just a moment. WIMPs were originally an explanation. Maybe there are some particles that we haven't yet found that are massive, and they don't interact very strongly, and that's why they don't produce light or absorb light. So weakly interacting means they don't do the things that normal atoms do and interact strongly with each other and with light. So weakly interacting massive particles came along first, and they were just abbreviated to WIMPs. Some physicists said, well, I'm not going to work on WIMPs. I want to work on something that's much more, what's the opposite of a WIMP? A macho. So they took macho and then reverse engineered the acronym to come up with massive astrophysical compact halo objects. So let's deal with these two candidates. Let's deal with them in that order. What do we mean by a macho? Well, these are objects. Okay, fine. They're massive because if they weren't massive, they wouldn't give us the gravity we need. They're astrophysical. Well, that just means there's something out there, and that's just a good excuse for getting the A into the acronym. So what do we mean by a compact halo object? Well, a compact halo object simply means a relatively small in terms of physical size, object in the halo of a galaxy. So a disk galaxy, for instance, will have a nucleus. It might have a very clear, distinct disk, but generally speaking, it'll have a spherical halo around it, which will contain a certain amount of gas and, for instance, in the case of the Milky Way, quite a large number of globular clusters that we can see as well. So a halo is the spherical region immediately around a galaxy. So a macho is an object which is quite massive and exists in the halo of the galaxy. It is hypothesized that maybe these could be objects made of normal matter. Simply normal matter that doesn't seem to be emitting much light. We would then have to worry about whether they absorb light, but let's just for the moment assume that there are objects out there, some astrophysical bodies made of normal stuff, but they simply emit very little light, such as black holes, neutron stars, or white dwarfs. It might seem odd to put white dwarfs into that category, because surely white dwarfs are white. Well, yes, they start their life as white dwarfs. If we think of the sun coming to the end of its life, once it's blown off its outer layers as a planetary nebula, the core of the star that's left is a white dwarf where no more nuclear reactions are taking place. So it can't stay hot. It starts its life hot, but it basically just cools down because there's no more thermonuclear fusion reactions going on in the core. So a white dwarf will very quickly become dark, effectively a black dwarf. So if they don't emit light, how can we detect them? Well, one possibility is gravitational lensing, not on the scale of a galaxy as we saw before, but so-called microlensing, lensing from small objects. If we imagine we're looking at light from a distant star, some of that light will reach us on Earth and we see a certain amount of starlight. But we can ask the question, what happens if a black hole or some such object happens to drift into our line of sight? If a black hole happens to line up with our view of that distant star, then some of the light from that star can be lensed or focused by the black hole, and hence we get a brightened image. And as that black hole happens to drift across our line of sight, as it moves away, we get back to status quo and the light from the star goes back to normal. So if we were to look at a distant star and we see the star's light doesn't seem to change, but then very briefly gets brighter and then goes back to its normal state, that could be a sign that something has moved in front of the star and has focused the light from the star. Now, stars will always change their brightness. If a star has an exoplanet, for instance, that will change the light, but that will result in a dip of the light, not an increase in the brightness of the star. Of course, it's very unlikely that we are so lucky that a black hole happens to drift in front of our line of sight for a given star. So for this to work, we would have to look at not one or a dozen or 100 stars. We would have to monitor the brightness of millions of stars in the hope that some black holes might be drifting in front of them and we would see this microlensing. So that experiment has been done. This is the Milky Way as seen from the inside, but let's imagine it as seen from the outside. If we imagine we're looking at the Milky Way, there's the galactic bulge in the galactic centre. We are sitting quite some distance out from the centre, and there are the Magellanic Clouds there, the large and the small. If we were, with our telescopes, to stare at stars within either of the Magellanic Clouds, millions of them, if we were to stare at them and measure their brightness over a period of time, we might expect some of those stars to suddenly brighten if the halo of our galaxy is full of black holes, which would account for the existence of dark matter, the matter that we can't see. Remember, there would have to be an awful lot of them because we're trying to find a mass which is greater than the visible mass. The total mass of these objects would have to be greater than the mass of the Milky Way itself by a factor of 4 or 5 or 6. So if there's that many black holes out there, let's stare at stars in the Magellanic Cloud and see how many of them brighten over a period of a year or a few years. That experiment has been done, and what was found? Yes, some stars do show this effect. So yes, there are black holes floating around in our galactic halo, but not enough. It's estimated that the machos that have been discovered by this technique can account for perhaps a few percent of what it is we're looking for. Given that we know roughly how much dark matter is out there, black holes don't appear to account for that percentage. Some people will argue, maybe the black holes are so small that we're hardly going to get any gravitational lensing. That is a possibility, but it would appear that machos do not exist being made up of large black holes, sort of stellar-sized black holes, in enough numbers to account for dark matter. So we come back to the other alternative, WIMPs, weakly interacting massive particles. Meaning particles which we really haven't discovered yet. They're not protons, they're not neutrons, they're not electrons, they're not any of the particles that we have already discovered over the last century or so. They are relatively massive because they're going to have to make up quite a large mass in the universe, but they don't interact very strongly with anything else, hence weakly interacting massive particles. They interact through gravity. They have to, because that's what we're looking for, remember. We're looking for something that produces gravity, so they have mass, but they don't interact through electromagnetism. They're similar to particles that we call neutrinos. They are very lightweight particles, so we think that these WIMPs must be similar to neutrinos, but much heavier and generally moving more slowly through the universe. Presumably they were made in the Big Bang, because it's really difficult to see how they could possibly be made after the Big Bang, which was the origin of essentially everything. That's the subject of a different talk. And it's thought that if these dark matter particles do exist, then maybe they annihilate with their antiparticles. Our understanding of the universe is that every particle has an antiparticle. Electrons have anti-electrons, protons have antiprotons, quarks have antiquarks. So if a dark matter particle exists, it will have an anti-dark matter particle, and it's possible that they annihilate. We believe if these weakly interacting massive particles do exist, they might conceivably be concentrated in the core of the sun, because that's a big gravitational well, and they do interact through gravity if nothing else. Therefore, they might be attracted by the sun and end up captured by the sun, at which point they may annihilate and produce other particles which we hope to detect, for instance, neutrinos. So the bottom line is we have to go searching for either the particles themselves. Can we make experiments that allow us to detect weakly interacting massive particles? Or perhaps we ought to go hunting for the signs of these WIMPs annihilating with anti-WIMPs and producing other particles which we understand like neutrinos. Okay, so let's have a look at some of the experiments that in principle are looking for WIMPs or the effect of WIMPs. One of the largest is the so-called LZ experiment, the Lux-Zeppelin experiment. It's a large tank of xenon. Xenon is a very heavy atom, which is ideal. It's a very heavy atom and it's a very dense liquid, and it's a transparent liquid, which is important for what I'm going to show you. And the idea is, if a dark matter particle comes into this tank, we have a chance of detecting it. Let's have a look at a little video that shows how that works. Right at the heart of the experiment is a container with 7 tons of liquid xenon, and it's surrounded by shielding. So right in the middle there we have xenon, and if a dark matter particle comes in and hits one of those xenon atoms, it can actually produce a flash of light and a few electrons, which then drift to the top of the chamber and interact and give us another flash of light. So a dark matter particle flying through this chamber can give us a signal. But unfortunately, there's loads of background particles which will confuse matters. So ideally, we want to shield this with some scintillator to tell if other particles are coming through, and a big water tank to act as a shield to try and prevent any other particles interfering with our experiment looking for dark matter particles. We also surround it with rock and put it at the bottom of a very deep mine shaft, because right at the top, that's not supposed to represent rain. Right at the top here we have cosmic rays which are continually bombarding the surface of the Earth, and most of those will be stopped by a few hundred meters of rock. So we put our experiment in the bottom of a mine shaft a kilometer or so underground to try and eliminate any background particles that we are not interested in. Hopefully then we will only see the resulting flashes from dark matter particles going through our experiment. Another way of doing it, the previous one is one of the largest and most sophisticated. Here's another one that's been operating for a few years. This one is in Japan. The previous one, I forgot to mention, is in a mine in South Dakota in the USA. Here's a large experiment that's being carried out in Japan, a large tank of water. And the principle here is, well, you know that when an aircraft flies faster than sound through air, what happens? You generate acoustic shock waves, because effectively the air can't get out of the way fast enough. So you get a sonic boom when you travel through air faster than sound can travel through air. But it's also possible to travel through a medium faster than light can travel through the medium. You can't go faster than light in a vacuum, but if the light is going through water, you can travel through water. You can have a particle traveling through water faster than light can travel through water. And then you get the analog of a sonic boom. You get a photonic boom called Cherenkov radiation. That's why nuclear reactors glow blue. It's not just Hollywood thinking that looks really cool. That is the light you get. It's a photonic boom. It's because particles coming from this reactor are traveling through the water faster than light can travel through the water. So what happens in this big water tank is you're looking for a particle that's coming through really fast, which produces a flash of blue light, which is then picked up by loads and loads of photosensors which are lining the inside of the water tank. And that's what it looks like when you've drained the water out. And if you're having difficulty with the scale, there's still a little bit of water at the bottom of the tank there, and there's 2 people in a dinghy. So you can see just what the volume of this water tank is, and you get a feel for just how many thousands of light sensors there are on the inside of this tank looking for this characteristic blue flash. It may not be from a dark matter particle, it may be from the result of a dark matter particle annihilating with an antiparticle and producing, for instance, neutrinos, which then go flying through this tank, producing the blue flash, which tells us something very energetic has just come through. That's what the sensors effectively look like, small photocells effectively, each of which is recording a very brief flash of blue light. But it works not only with water, it also works when the water is frozen. And so, as well as experiments such as the one I've shown you in Japan, there's a similar experiment but with ice at the South Pole. So this so-called ice cube laboratory is sitting on top of the Antarctic ice pack. And they have drilled down into the ice, effectively all the way to the bedrock. And if you're having a little difficulty with the scale there's the Eiffel Tower, just to give you an idea of scale. The ice cap is of order 2.5 kilometers thick. And what they've done is drill down into the ice and again instrument it with loads of these photosensors, so that if any particle passes through the ice, it'll produce a blue flash, and then these photosensors will pick that up and you'll be able to tell that an energetic particle has come through your detector. As well as being possibly concentrated in the sun, because WIMPs will be attracted to gravity wells, there might be a lot of them at the centre of the Milky Way. Remember, there's a supermassive black hole at the centre of our galaxy, so maybe WIMPs will be attracted to that part of the Milky Way. And it's thought that if there is a lot of dark matter in the centre of the Milky Way, it might produce gamma rays when they annihilate with their antiparticles. And so there are experiments planned to search for gamma rays produced by dark matter annihilation. There's our picture of the Milky Way again. Remember, the centre of the galaxy is here. That's rather difficult to see from northern latitudes such as the UK because it's rather low on our horizon. But if you have a telescope in a different part of the world, that the galaxy's centre of our galaxy is higher in the sky, and hence you might be able to pick up particles from it. So there's a so-called Cherenkov telescope array, looking not specifically at the centre of the galaxy, but looking into the sky to see if there's any blue flashes that tell us there are particles coming from any given direction. This is a cartoon before the CTA was actually put together, showing it in, apparently, Monument Valley in the USA. In fact, it's actually been built in, some of the telescopes are being built in Chile, and some of the telescopes are being built in the Canary Islands to spread the telescopes across the north and south hemispheres. And what they're effectively looking for are blue flashes in the sky. And if you work out which telescopes can see the flash, then you can figure out which particle has come in, how much energy did it dump into the atmosphere, and from which direction did it come. And then you might be able to figure out whether these particles are coming from the direction of the centre of the galaxy or not. There are loads of other experiments going on, all at different scales, all organised by different countries. There are dozens, possibly even hundreds of experiments going on around the world trying to detect dark matter particles. For instance, picking out a few almost at random, there's one in Italy, there are others, there are some in Canada, there is some going on as a collaboration between France and Italy, and a number of different sites throughout the world. Many of these experiments have observed something, but so far none of them have given us a definitive, yes, we have found the dark matter particle or evidence of a dark matter particle. So far, all of the results that have come from these various experiments are either contradictory or simply have not yet been confirmed. But there is another possibility. As well as is it WIMPs, as well as, well, is it actually machos? There is a third possibility, and that is we have simply misunderstood how gravity works. In other words, we only seem to need dark matter because we've got our sums wrong. We've actually calculated things incorrectly. Maybe gravity works differently on the scale of the universe and the scale of the galaxy and the scale of the solar system and the Earth and the Moon, etc. So when we think we're calculating the gravity from a galaxy cluster, maybe we're not doing it right. That means you have to modify gravity depending on the scale at which you're working. In other words, it's not universal, it is scale dependent. So there is a theory called modified Newtonian dynamics that says gravity works differently on different scales. And you can't simply scale up the gravity we understand from the solar system and then get that to work on the scale of a galaxy or the scale of a galaxy cluster. So you can, if you like, tweak gravity until it fits the facts. But unfortunately, modifying gravity gives you all sorts of other problems. Sometimes you can modify gravity so it works fine on a cluster scale, but then it doesn't work on a galaxy scale. You can modify gravity so it works on the gravity scale, on the galaxy scale, but then it doesn't work on the cluster scale. Finding a modification to gravity that works on all scales and doesn't introduce any other problems of its own is still in itself a problem. So there are still people working on modified Newtonian dynamics, but many people believe it's a dead end. We should concentrate on either finding machos or finding WIMPs. So does it matter? Well, simulations of how the universe behaves can give us galaxy distributions, in other words, large-scale structures of the universe that are similar to what we believe is actually out there. But if we don't include dark matter in the simulations, then the simulations simply don't work. We live in a universe which started apparently about 13.8 billion years ago, and during those 13.8 billion years, gravity has taken small variations in density and produced all of the stars and galaxy clusters and superclusters that we see today. If we don't have dark matter in the mix, we can't get everything to clump together fast enough to give us the universe we see today in only 13.8 billion years. If we imagine what the observable universe is like, at the moment, the observable universe is a sphere of diameter about 100 billion light years. But we know the universe is expanding, so we can hypothesize that, well, if we go back far enough, everything that we currently see in the entire observable universe used to be only a few centimeters distant from each other. It's difficult to get your head around anything that is now 100 billion light years in diameter ever being a few centimeters in diameter. But that, we believe, is possibly how it started. And this early cosmic golf ball, if you want to think of it that way, had dimples in it, just like a golf ball. Not dimples in the surface like a golf ball, but dimples in the sense of small variations in density and temperature. And over billions of years, gravity has taken hold of those small differences in density and has resulted in the cosmic web of filaments and voids and galaxies and galaxy clusters that we see today. Here's a little bit of a simulation. The link is at the bottom if you want to look at these videos for yourself. We've taken a chunk of universe, not the entire observable universe. We've taken a chunk of it and we've seeded it by saying, let's assume that there's mass in there, but small variations in density, not perfectly uniform. Small variations in density, and then we're just going to leave it alone and let gravity do its stuff. And over billions of years, gravity makes the denser parts even denser. They look bright in this simulation. And some regions become darker, indicating that they are underdense or almost empty. And we see galaxies and galaxy clusters distributed not uniformly, but we see them occurring in, if you wish, filaments, these lines of structures, and this web-like structure exists throughout the universe. And some regions, like this region over on the right-hand side, appear to be relatively devoid of galaxies. And when we look out into the universe, this is pretty much what we see. We see a cosmic web of filaments, and each of these filaments is comprised lots of galaxies and clusters of galaxies. And we see some regions of the universe that appear to be relatively empty. So we can understand the large-scale structure of the universe through these simulations, providing we put dark matter in. If we don't put dark matter in, the universe doesn't collapse into this structure fast enough. In other words, 13.8 billion years isn't long enough for this sort of structure to evolve. So it looks like we need dark matter in order to live in the universe in which we live. If we look on the largest scale, it's a sort of foamy or web-like structure. And if we zoom in, we can see more and more detail in these simulations, and we zoom in to a knot in between two filaments, and we see ultimately we can resolve that into galaxies. So we have a reasonable handle on how the universe has come to look the way it has, but only if dark matter exists. So I've been trying to tell you how dark matter interacts, in the sense of it interacts with gravity, but it doesn't interact with light. I've shown you 3 out of the 4, and that's in the handout, pieces of evidence that it exists. I've asked the question, is it machos or is it wimps? But the bottom line is the jury is still out. We haven't found enough machos, and we haven't yet found a particle which we can declare as this is the dark matter particle. And does it matter? Well, our simulations of cosmic evolution say without dark matter, probably we wouldn't exist, because the universe would not have evolved the way it did. So I've told you why it's dark, and yes, it does matter. Thank you very much for listening.